So I guess the next conversation we need to have is how do we find the overall resistance or reactance or whatever we want to call this of the entire circuit? I guess we need to get our nomenclature and our vocabulary settled out because it's improper for us to say, refer to a resistance as a reactance or a reactance as a resistance. I mean, they kind of behave the same way, but they're not really fundamentally the same thing. So I guess we need to come up with a new word. So we'll go back to our thesaurus, flip through some stuff and figure out the word impedance pretty much means the same thing. It affects the current and kind of hinders it, right? And hurts it. So we're going to have to come up with some kind of a way to determine what is the total impedance of a series circuit that contains, I guess, a generator that's got an EMF. We'll put it in R, L, C kind of circuit. This will be our R, our L, and our C. When it comes to figuring out things like doing Ohm's law, I guess in principle, we could say that the EMF is equal to the total amplitude of the current, and this could be peak or RMS, it doesn't matter, times whatever this new impedance is. And I don't want to call it R or X. So I guess we'll just call it Z. So this would be the definition of impedance. It works in Ohm's law just like all the other ones do, but now we have to figure out how are we going to find that? If we were to do this with, say, just regular series rules of adding the voltages together, this would be straightforward, right? Because we could just do the series rules. We could apply Kirchhoff's loop rule, for instance, and work our way through it and get an answer. But we have a little bit of a problem because I know what the amplitudes are for VR, VL, and VC, according to V equals IR, V equals IX, whatever. But because they're not simultaneous due to ELI or ICE or just the resistor doing what the resistor does, that makes it really complicated because Kirchhoff's loop rule applies. But when we're offset by these phases, that's going to be really complicated. So it might be useful for us to represent this in a slightly different way. And that's where the phasor diagram comes from. So first things first, it is possible for us to represent some kind of a sine wave as just a vector spinning in some kind of space. And we'll call that a phase space. As for why that works, I guess we could skip forward a page and say, look, if you have a sine wave that looks like this, right, it's defined as a sine of some angle, which is really some kind of an angular speed or angular frequency times t. So what does the angular speed really represent? Look at it this way. I could represent this sine wave as some kind of a vector that's got an amplitude, right? So this would be a sine theta, and that's like x. And I can say, let this thing rotate in a circle in some kind of this phase space. And we'll say, let's define the x. If we're going to say it's a sine, then okay, here's your angle. The sine of it would give us this component. So as this thing rotates, we're seeing the x component of it go out to its max, come back, go to this other max, and it's doing this as the vector is rotating in the phase space. Another way that might make this a little bit more digestible or intuitive, if we had, say, a turntable, which is going to date me also, but just like a record player, if I've got a thing on it, and it's going around, you can see clearly this is something just rotating with an angular speed. But if we were to flip this on its side and do this, what you're really looking at is a shadow of something in simple harmonic motion as it goes through. So hopefully you're convinced that a rotating vector, if we take one of its components, it can really represent this. This is really what we talk about too. It's not the same kind of a phase space, but we know that numbers have a modulus, right? So the value of the number. and it's got its real part, and it's got its imaginary part. So when we want to focus on the real part, we're doing pretty much that. This value can be anywhere in the complex plane, but we only look at the real component of it, and that's this part. So the key for us to understand, how are we going to deal with this impedance where things are 90 degrees out of phase with each other, whether it's L, C, or maybe R, we need to represent these geometrically, not algebraically. So it's not going to be as simple as just doing number math. We're going to have to do some kind of geometry. Okay, if that's the case, I want, maybe we'll make this the origin. I need something that is a reference for the other things in the phase. I know by the rules of series that the current is the same in all of these components all at the same time. The voltages are a little different, but the currents are all the same. So if that's the case, why don't we just say, here's a vector, and it represents the current. So from this part, we need to ask ourselves, what do all of the voltages look like measured relative to this current? So in calculus, we tend to make things go in the counterclockwise direction. That's because it's a right-handed coordinate system, right? So as we close our fist, things do that. So if you ever did contour integrals or something in an advanced math class, that's why it's always taken to be counterclockwise. Let's give ourselves a reference point too. I'm going to just be sitting here at some point. Let's say I'm looking from this direction. All right, so that's kind of an eyeball. So as this thing rotates, every cycle, I'm going to get smacked in the eye by this eye vector as it comes around. So that's just me seeing when the current happens is when it meets me. Okay, of all the components, let's focus maybe right now on the resistor. Is the voltage on the resistor synchronous or asynchronous to the current? I know it happens at the same time. Oh, my markers are going bad. So this will be VR, right? And we know it's, what is all this junk? We know that the resistance is synchronized. Do I have anything better? Maybe I'll do, hopefully this is better. Not really, but we'll make it work. Okay, next one is, let's focus on the inductor. So I'll say the inductor is orange. What do we know? Is the voltage on the inductor going to hit me in the face first or second? And I guess we need to go to Eli, the Iceman. E is for EMF. For the inductor, it happens first. So that means I need my voltage on the inductor. I guess it needs to be over here. So that as these rotate, boom, I get hit with the voltage first, and then later in the cycle, I get hit with the current. Okay, so that leads, and then the capacitor is ICE. The current needs to hit me first, and then 90 degrees later, I need to be hit by the capacitance. So this is our phasor diagram, and it can be useful to geometrically get, you know, what is the net value of the EMF and the induction, and not inductance, the impedance and all these other things. This phasor diagram by itself is not really useful because I have Y components, if we want to call this Y, but I don't have a well-defined solid kind of X value. I guess the way I drew this, VL looks a little bit longer than VC. So what I really need to focus on is some kind of a vector that is a combined sum of these two. So if this is VL and this is VC, why don't we take away a little bit? That's VL minus VC. Now that might be more useful. And maybe I'll redraw it down here. This is VL minus VC. And then I've got VR up there. Okay. So when we look at these, it looks like I need a new color. This is the total net voltage of the entire system. And what would that be in some kind of a series circuit? All the voltages we know add to the source. Here they're adding geometrically because they're not in sync with each other. And we have this arrangement. So the total voltage, I guess, is the EMF from the generator. And maybe if you don't like that, we'll call it E generator. We should remind ourselves where the current is. I is pointed that way. So what are some things that we see immediately? How would I find the total EMF based on these things? It's a Pythagorean theorem, right? So the generator squared equals, looks like VR squared, plus this quantity, VL minus VC squared. Yeah, okay. So if we wanted, we could say E gen is, it looks like the square root of VR squared plus VL minus VC squared. So that's interesting. Is it useful to helping us find the reactance? Well, each one of these is really E is equal to IZ, right? Or V equals IR, or V equals IX. So really all of these have an I in front. So that's IZ is I squared R squared plus I squared, I guess, XL minus XC quantity squared. And we know that these will cancel. So in the end, in series, the impedance is the geometric sum or the vector sum of these. And that's a plus, not a minus. So that looks interesting. What else do we see? Maybe I can shift this up and hopefully keep it in frame. Surely there's got to be more useful information that we can pull out of this analysis. So what do we notice here? The EMF is offset from the current by some angle. Maybe not theta, let's call it phi. That's the phase angle. How out of sync is the current to the EMF on the generator? So we have other means. Let's say, what's the tangent of that? It looks like this voltage, right, is opposite VL minus VC over the adjacent side is VR. And if you like, we can call it IXL minus IXC over IR, and all that stuff cancels. And here we get this formula. So here's how we find the phase angle. All of this stuff comes from just doing a little bit of trigonometry and thinking about these as vectors, not as, sine functions or something. So I think we're good. There's not a lot more to discuss about that. Whenever you see these, some advice that I'll give you: if you were to say have a circuit that was only RC, would you necessarily just throw this out and call this 0? I don't know, right? Because if you have no L, maybe it works out that way. But there is a problem of calling C equals 0, and then you'll end up having an infinity here that doesn't work. So my suggestion to you, if you don't have a component in the circuit at all, just throw out that reactance, because it doesn't exist in any capacity, right? So if this is an RL circuit, or let's say an RC circuit, that's your formula, R squared plus XC squared. If it's only RL, looks like that. If it's only an X, or if it's only an L, it looks like that. Everything boils down to Z equals some combination of these in series. This phasor diagram would be a little bit different in parallel. And I'm not going to do the full analysis, but in parallel, what are the things that are all the same in parallel? If you had like R, L, and C. Well, it's not the current, it's the voltage. So in that case, we would make this the voltage on the generator. And then you'd have to ask yourself, okay, well, this is I for the resistor. And then you have I for the capacitor, and inductor is one of these two, right? You'd have to do ICE and ELI to figure out which. So that would be the treatment for the capacitor. To discuss an interesting finding, and then maybe some misconceptions that happen along the way. Let's say I wanted to maximize the current flow in a circuit, right? So if I have E equals IZ, which you know is I times this combination, R squared plus XL minus XC squared. If I wanted to maximize I for a given generator formula, what would be the situation that would cause that to happen? I will never, ever, ever, ever get the Z down to 0 because this R is always here, right? So I can play around. Let's say that in this case, we can change the frequency. So I'll make that variable. What are our possibilities if frequency is allowed to change? This is being a difference. It's possible that I'm a little more inductive than capacitive. I can change those ratios and make it more capacitive than inductive. Or here's a case right here in the exact center. Hey, if these are exactly equal, then this piece goes to 0. The resistor is just R, so that's Z is equal to R. But if these are anything other than perfectly equal, there will be a remainder. And that will add to R and make Z larger. So we can say, if I wanted to maximize I, we must minimize Z. And Z minimum is equal to R when XL is equal to XC. So that's a special condition to maximizing the current in this case. Let's play with that. What was XL? I think it's omega L. And what was XC? I think it's 1 over omega C. So I could rearrange these. And then I could solve for this. And what do we find? That's the resonance condition. And we got that before, just playing around with driving something in its own natural frequency makes it happy. So this resonance condition can easily be rederived or discovered from saying, what do you want to make I max, make Z min? That's possible if these are equal. How do you make them equal? The frequency inside has to be the natural frequency to get the best results. All right. So just some kind of stuff on the side, maybe some puzzles and things that you should think about. Has anyone ever used a variable LC oscillator, one that you can change the frequency, change its magic frequency to match a particular driving frequency of some kind? So let's say that I have some kind of a driving frequency here. And if I matched up with it, let's say this is all the frequencies. No, this is the, let's say that's a resonance frequency. As you do this, we know we'll get better results right here, where here the circuit is more, I guess, capacitive, because the capacitor is dominating at low frequencies. And here the circuit is more inductive, and right here in the middle, this is that balance, right, where they kind of are at a compromise. And it kind of keeps them both not as happy, but as least upset as possible. If I had something that would change the resonant frequency, then that would change where this peak happens, right? So I can tweak the peak by changing either L or C in some way to shift this peak left and right. And if I had, say, some kind of an external source, let's say I had multiple sources. Here would be source 1, source 2, and source 3. And they're all at different frequencies. And let's say let's just name the frequencies, right? How about 96.3 and 101.5 and maybe, I don't know, 88 something kilohertz. And let's say I wanted to build some kind of a strange circuit where the current would really let us know what the signal does, and maybe we can hook it up to something that we want to use as a detector, right? And if we have an LC oscillator whose magic frequency can be changed either of two ways, I can have a variable L, which is as simple as putting a slider on a ferromagnetic material that can be, plunged into or out of the inductor, and the relative fraction changes mu, right? So that's a variable L. I guess maybe a variable C would be one where one of the plates looks like a half circle and the other plate is a half circle, and I put them on a little dial, right? And I can just twist them clockwise and counterclockwise to change the area of the plate. So this is a variable C with a variable A. And this inductor could be, I don't know, we had that ridiculous formula, but it had a mu in there somewhere, right? So I can just change it and then stuff. I hope you're figuring out what this device is. It's a radio tuner. The antenna is being hit by electromagnetic waves, and all these three frequencies are competing for the attention of the circuit. All of these waves are hitting the antenna, and it's essentially turning the antenna into a generator. The fields force the electrons to one side and then drives them back, right? And even though the generator is not a closed circuit, inside this long wire, we've got some kind of a force that's trying to get the electrons to move. But the problem is the inductor and capacitor are gatekeeping. Like what electrons are allowed to move, it depends on their speed. So if I was trying to say, what do I want to listen to? It's just a little bit too early in the morning coming into work for DMX. I found that that's not true working at home. Every hour is the right hour for rap from 1995. So I don't necessarily want to listen to that. I know this is the rock station, but I'm not in the mood for it. But maybe I want to listen to, say, Elvis Duran or something like that in the morning. I would want to tweak either my L or C if I have a slidey type or a twisty knob type to kind of change where is that frequency maximally satisfied. That's really a bad picture. There. I am now tuned to this particular station, and then that means any currents that are oscillating at this frequency are the ones that will be picked up and will be allowed to pass through the L and the C filter. And those currents will go to my speaker and cause the cup to vibrate with the same frequency. Anyone notice that radio stations just happen to be the same integer apart? Like two adjacent stations can't be too close together. Like they're always like 0.2 megahertz or something like that apart. Megahertz, not kilohertz. That's not a physical limitation, it's a governmental one. Let's say I wanted more stations. So we've got the stations between the stations, right? And pirate radio is going on. That can be somewhat problematic because the station I really want, it's coming in pretty loud and clear, but I'm getting amplitudes that are not negligible from, in this picture, 1, 2, 3 more stations on one side and 2 more on the other side. So I'm listening to 6 stations all at once, and they're all letting my speaker move at their frequencies. We don't want that. So we don't want interference from the other stations. That's why the FCC regulates only certain frequencies are allowed, and they all have to be split a certain distance apart. So we don't get this kind of crosstalk going on in between them. And EM waves are fascinating and will be coming up next after the LC circuits.